This is a presentation of the recent work by E Alba, Pachos, and García-Ripoll titled Winding Number Order in the Haldane Model with Interactions, to appear in New Journal of Physics. In our work, we consider a two-dimensional topological insulator. As an example, we take the Haldane model, which is a particular instance of the anomalous quantum Hall effect. This model is defined on a honeycomb lattice occupied by fermions with complex hopping amplitudes. In presence of periodic boundary conditions, a topological insulator exhibits insulating bulk with non-trivial winding number. When it has open boundaries, then the non-trivial winding number causes the presence of gapless edge currents traveling along the boundary. The question we want to address is what is the effect of fermion-fermion interactions in the topological properties of the model. The Haldane model is given in terms of a honeycomb lattice with spinless fermionic modes positioned at its vertices. The honeycomb lattice is bicolorable, consisting of a red triangular sublattice and a blue one. In a cold atom implementation, these two lattices could be represented by different atomic states. The lattice is periodic with respect to a two-side unit cell. The fermions can have complex hopping amplitudes between nearest as well as next to nearest neighbor. Hence, the single particle Hamiltonian of the model, obtained by a Fourier transformation, is given in terms of a 2×2 matrix. The energy dispersion relation of the model across the Brillouin zone is given by a single conductance and a single valence band, depicted here by blue and red colors respectively. The ground state of the model is obtained by occupying with fermions all the negative energy states. As the one-particle Hamiltonian of the model is a two-dimensional matrix, its ground state is efficiently parametrized by a real three-dimensional vector, which is a function of momentum. The topological properties of the model are determined by the winding number of this vector as the momentum takes all possible values in the Brillouin zone. When the system is in a non-topological phase, then the vector can cover only the lower half of the Bloch sphere or only the upper half. In both cases, the winding number is 0. If, on the other hand, the unit vector spans the whole sphere as the momentum spans the Brillouin zone, then the winding number is non-zero, thus signaling a topological phase. Let us now turn on the interactions between fermions residing at nearest neighboring sites. For moderate values of the interactions, the winding number does not change. If we increase the strength of interactions, then the ground state vectors are all aligned along the given direction, thus giving a trivial winding number. We explicitly evaluate the winding number that can take values +1, 0, or -1 for a wide range of couplings. This we do both numerically with a DMRG simulation and analytically with a mean field theory. In these plots, phi is the complex phase in the hopping amplitudes of the Haldane model, and u is the strength of interactions between fermions. We observed that both the numerical and the analytical results are in good agreement. They show that the winding number is largely resilient to the presence of both attractive and repulsive interactions.